objective 8, I taught you how to set up a problem, and for this first set of problems, we're going to solve using graphs. So I'm going to show you and go through two examples, problems 1 and 2. So if you can get out your kinematics problem solving with graphs, I'm going to show you how to solve using graphs. So we're not using the Fab4 that I talked about yet. We'll be using those in the future problems. So looking at number 1, I'm going to go through how to set up a problem and how to solve it. And I'll go through another example in example 2 because it's slightly different. Alright, remember the first thing to do is to read through the problem and then draw a motion diagram. So it says a race car speeds up from 44 meters per second to 66 meters per second in 11 seconds. Alright, so there's a lot of information there. So we're going to draw a motion diagram. We're going to go ahead and draw the detector. I always start with drawing the detector, and I just use a triangle for the detector. And it starts off from 44 meters per second to 66. So I know it's speeding up, and I know the arrows have to get longer. So at least draw 3 arrows, remember. It's speeding up. It doesn't say direction, so I'm just going to go to the right. You can choose if it doesn't say. Then remember there's those list of variables, so if you have to, you can go ahead and look at objective 8. We have the original velocity, and I always draw this where it's starting. We have the final velocity, and I always write this where it ends. And then we have the acceleration to look at, distance, and time. So we have those things to look at. So I always write down those labels, and this is all worth points, so make sure you get this down. Alright, so reading the problem, meters per second. Meters per second is a unit for velocity. So it says this is where it starts from. So I know that this right here is the original velocity. So I'd mark this 44 meters per second. The final velocity is 66. I know meters per second is a unit for velocity, so I plug in the 66 for the final velocity because that's where it ends up. In 11 seconds. So seconds I know is a unit for time, so I'm going to plug that in for time. Alright, I don't know the distance. I don't know the acceleration. However, I can always figure out the direction by looking at the motion diagram. So I see it's going faster to the right. That means a force would have to push it to the right to make it go faster in that direction. So I know the acceleration points to the right. As a result, I know it's positive because it points away from the detector. Alright, so that's your first step. The next step is to think about the graphs, and this is probably the trickiest part of the problem-solving process. So we have something starting close to the detector, so with distance, think of how close it is, and it's going away. So it's going to start down here, and it's going to head away. Well, how is it going to head away? Well, it's going slower and faster. Remember, speed, the rate of speed, is the slope of that line. So if it's going slower, it's flatter. If it's going faster, it gets steeper. So you want a line that starts close to the detector here. Pretend that's the detector. It's going slow, so it's going to be flatter. Then it's going to get steeper as it goes faster and faster. So it's a line that curves upward. Alright, so looking at this, I'm heading away, so I know my velocity is positive. The thing is it going to go up as a straight line away from 0 or towards 0? Well, let's think about it. It's going 44, so it's not going to start at 0. It's going to start here. Call that 44. And then it's going up to 66, so we'll call the ending up here 66. And it's positive because it's heading away. So we're going to go ahead and do that. And it says it does that in 11 seconds. So both on the timeline there, we can write 11 seconds on all of these because that's how long this is traveling for. So then, what you want to do is think of the acceleration. Well, the acceleration we already know is positive by looking at the motion diagram. And if you look at the slope of this guy, it's positive. And remember, acceleration is a horizontal line. So it doesn't matter what it is. We don't know what the number is, so I'm just going to go ahead and draw a horizontal line. Sorry, that should be horizontal. And we don't know what it is. We just know it's positive. Okay? So that's all we know so far. We also don't know the distance. We weren't given that, so that's a question mark. So make sure you have your labels on each of the axes, so double check them because that's all worth points. Alright, so then for part C it says use the slope of all the graphs in the area under the curve of a velocity versus time graph to figure out the missing information. So we got to figure out acceleration and distance. Alright, well let's look at the velocity versus time graph. We have a line here that's going upward, and if we look at the slope of that line, that tells us the acceleration. So I know the acceleration is going to be the slope, so it's the rise over the run of the velocity versus time graph. So we're focusing on this middle graph. This is an important graph for these problems. Alright, so I know the acceleration is the rise of this line. Well, how far does it go up? Well, it goes from 44 to 66, right? So how many meters per second does it go up? Well, 44 to 66, you can subtract them. You get 22 for your rise. And then your run is 11 seconds. So this goes over 11 seconds. So you got 22, if you want to look at units, you got 22 meters per second over 11 seconds is the run of that line. So then you get 2 meters per second. And we can actually have 2 sig figs here. I'm just going to do sig figs. I'm not as worried about this chapter, but I'm going to use sig figs. So it's meters per second, which is meters per second squared. So there, I just figured out the acceleration by looking at the slope of this line, rise over run. Alright, well how do I figure out the d, or distance or displacement? Well, we also know by looking at this middle graph, the area underneath this curve is going to tell you the distance or displacement. Well, since it doesn't go down to 0, it's a little bit trickier because we have this triangle here, and I'm going to change the color so you can see the pieces. We have this triangle right here, and then we also have this rectangle right here. So if we find the area of those two different pieces, then we can figure out the displacement. So we got the triangle and the rectangle to add up. So if to find the displacement, we're going to look at the triangle. It's 1/2 base times height. So it's 1/2. The base of the triangle is 11 seconds, so 11. I'm just going to put the units in there to show you that we end up with meters. And then the height of that triangle we know goes from 44 to 66, so it's 22. That's meters per second. So you can see actually the seconds cancel. And you end up with meters, which is great because that's distance. So we have that piece, plus we have the rectangle, and the rectangle is length times width. So it goes from 0 to 44. And that's meters per second, which you don't have to put the units in there, I'm just showing you. And then the width is 11 seconds. Okay, and you can see the seconds cancel again. So then you get these numbers. I'm going to pause it. Get the numbers just to do the math behind it. We have 1/2 of 11 times 22, and that's 121. Sorry, that should be 121. And then I'm going to switch to colors here, and then we got 44 times 11, and that's 484. Remember, these are both meters. So to get the total displacement, you have to add those up. So when you add those up, what do you get? Well, you get 605 meters. And it should only have 2 sig figs because we only have 2 sig figs for all of our numbers. So that rounds to 610 meters. Okay, so by using the area underneath the curve here, the rectangle and triangle, we're able to find the displacement. By using the rise over run of this line, we're able to find the acceleration. So that's how you use the graphs to solve problems. Alright, so now looking at problem number 2, I'm going to go through this one with you. We have to draw a motion diagram first of all. So brakes are applied. When brakes are applied, a speeding car slows from 45 meters per second for 10 seconds. The design of the brakes allows the acceleration to be negative 1.5 meters per second squared. Alright, so let's go ahead and draw a motion diagram. So we got the detector. I'll draw it up here. We've got the detector, and it slows from 45. So it's going to start off fast, and it's going to slow down. Okay, so that's the information we have. We have, remember, the original velocity, acceleration, that's an A, distance, and then the time, and then we have the final velocity. So we plug in everything we know. It slows from 45, so it starts off at 45 meters per second and slows down from there. Seconds is the unit for time, so for 10 seconds. And the acceleration we know is going this way, because you'd have to push this way to get it to slow down, which is negative, and it makes sense that our number is negative. So that's negative 1.5 meters per second squared. We don't know how far it takes to slow, and we don't know the final velocity after it slows down. So those are things we don't know. So we're going to go ahead and draw a distance versus time graph, and start off close. Remember the detector's right here, so we start off close, and it's going fast and then slowing down. So we want something steep and then flatter, so we've got steep and then flat, like that. And it's going away, so we know it's in the positive section. However, it starts off fast, and we know it starts off at 45. By the way, I forgot to label the time down here. The time is 10 seconds. We know it's 10 seconds on all of these. Okay, so it started off at 45. We know it slows down, so we know it goes down towards 0, but we're not sure what it stops at. We don't know the speed, the final speed. All right, and then acceleration, we know the slope of this line is negative, so it makes sense that it's negative. Also from the arrow, we know it's negative. So remember, this is a horizontal line, and we know this is negative 1.5. So make sure you have everything labeled there. That's meters per second squared. All right, so now we got to use our graphs to go ahead and figure out everything. So we know acceleration is rise over run of the velocity versus time graph. So if you look at the acceleration, we actually know the acceleration. We know a is negative 1.5, so I'm going to go ahead and write this in here, which I should have done. And we know the rise of this line. Nope, we don't. We don't know the rise of this line. But we know the run is 10 seconds. Okay, and we don't know the rise. So if we figure out the rise, we can figure out how much it goes up. So we can subtract that amount and get where it starts. So let's figure out the rise. And if you multiply by 10, it's being divided by 10, so if you multiply by 10, it gets rid of that 10, takes it to the other side. So to get the rise is negative 15. Just for a second. So if you look at that, it goes down 15. So you have to think of what's the final velocity then? Well, it's 45 minus 15, right? So if you do that, 45 minus 15, and that will give you 30. Since we only had one sig fig, we should only have one sig fig. The 10 only had one sig fig, so we should only have one sig fig. So the final velocity is 30 meters per second. So by using the acceleration is equal to rise over run, we're able to figure out our final velocity. So we can draw that on there now. That's 30. And then we can use the distance, which we don't know, is the area underneath this curve. So we can go ahead and use the two different pieces. We got the triangle again. You can kind of see the triangle right there. And then we have the rectangle down here. All right, so looking at the two different pieces, you got the triangle is 1/2 the base times height. And the base of the triangle is 10. The height, it goes from 30 to 45, so the height is 15. And then figure out that number, and then looking at the rectangle, the distance in the rectangle is length times width, because it's the area, so it's 10 times 15. At the rectangle, we had a width or length of 10, however you want to look at it. And the height of that rectangle goes from 0 to 30. So it is 30. So if you have the 30 times 10, that's 300. And then you get 75, 1/2 of 10 is 5, times 15. You get 75. So when you add that up, you get 375 meters total. And you should only have one sig fig because of that 10, so that should round to 400 meters. Sorry about that, writing off the page. There. So then we use the slope of this line to eventually figure out the final velocity. and then we use the area underneath the curve to figure out the displacement.